Hello, friends. Welcome to a gentle fall through the quiet rules of our world. Tonight, we trace the pull that shapes oceans, steers moons, and keeps our feet sure. Let your thoughts drift like leaves in slow air, settling wherever they wish. If the calm feels right, stay close and wander with us, and tap subscribe to be our companion on this slow, curious journey. A hush gathers around the night like the pause before a bell. In that pause, everything is falling, and almost nothing notices. Gravity holds oceans in their bowls and keeps air pressed close enough to breathe. The moon pulls at the seas and lifts tides by predictable hours. Each of these is a measurable fact, steady across years and instruments. Yet the story is richer than weight and pull. In free fall, astronauts feel weightless because they, their ship, and every bolt are falling together around Earth. The famous equivalence principle rests here. Acceleration and gravity can feel the same when judged from inside. A lift that rises with constant acceleration can mimic a planet's tug. A lift that falls can erase it. Another anchor sits deeper. General relativity describes gravity not as a push or pull, but as curved space-time shaped by mass and energy. Clocks on mountains tick a little faster than clocks at sea level. Signals from satellites arrive with delays that engineers correct each day, or your maps would wander by kilometers. On grander scales, light itself bows near the sun, bending by a small angle first confirmed during a 1919 eclipse. That bend is not folklore, it is geometry made visible. Even waves of gravity cross the universe. Detectors in long vacuum tunnels feel them as distances that change by less than a proton's width. And still the pattern stands out from noise. These ripples came from merging black holes, events far away and long ago, verified by timings that match the speed of light. Gravity runs through every hour you keep and every map you trust. It shapes stars, slows time, and writes delicate signatures into the paths of photons. Tonight we will set the pace low. You bring the curiosity. The facts will arrive softly and on time. Find a quiet place, loosen your breath, and let the story fall toward you at the same gentle rate everything falls. Gravity's instruction is plain. Without support, things accelerate downward at about 9.8 meters per second squared near Earth's surface. That rate sets how far a dropped key falls. Distance grows with the square of time, and how quickly a tossed ball curves back to your hands. Local variations nudge the number. The equator sits slightly farther from Earth's center than the poles, so gravity there is fractionally weaker. High plateaus shave another small amount. Deep mines add a touch. Engineers account for these differences, but the core figure remains close enough to guide bridges, fountains, and fireworks with quiet confidence. Air changes the story only at the edges. A feather drifts because drag balances weight at a low terminal speed. A stone reaches a higher terminal speed before drag matches gravity. Remove air and the distinction vanishes. On the moon, where the exosphere offers no resistance, a feather and a hammer land together. Apollo 15's simple drop made the point more clearly than equations, and the gray dust agreed without drama. Skydivers practice the same physics in air. They accelerate at first, then settle into a constant fall when drag equals weight, changing orientation to trim their speed like living control surfaces. Orbit is falling with timing perfected. A satellite travels forward fast enough that the ground curves away beneath it at the same rate it falls. The International Space Station circles every 90 minutes at roughly 400 kilometers altitude, moving near 7.7 kilometers each second. Inside, astronauts feel weightless because they and the station share the same continuous free fall. Weightlessness is not the absence of gravity, it is the absence of support. The term microgravity reflects tiny residual forces from air drag, rotation, and structural vibrations, small but measurable to careful instruments. These gentle jitters still allow protein crystals to grow smoothly and cold atoms to collect into record calm. Clouds. A moving path in orbit looks curved on a map, but is straight in space-time, a geodesic, guided by Earth's mass. Long before that language, Isaac Newton pictured a cannon on a tall mountain firing faster and faster. At the right speed, the shot never touches ground. It keeps falling around the planet. The idea survives translation to modern numbers. Too slow, and the craft re-enters, hot and brief. Just right, and it loops for years. Fast enough and it escapes entirely, following a trajectory that never closes. Weight and mass separate cleanly under this rule. Mass is inertia, the reluctance to change speed or direction. You carry the same mass on Earth, the Moon, or in orbit. Weight is a local force between you and a surface. In an elevator, a scale reads less when the car accelerates downward because support slackens. It reads more when the car speeds upward because support grows. The reading is a comment on contact, not on identity. The equivalence principle shapes the same insight more broadly. Free fall erases weight because everything nearby accelerates together. A dropped notebook, a loose pen, and your hands share the same curve, so they hover relative to one another until a surface interrupts. Projectiles answer to the same clock. Ignoring air, a ball kicked at the same speed travels farthest when launched at about 45 degrees, because horizontal and vertical components balance range and hang time. Real fields add drag and wind, but athletes still feel the geometry. Artillery crews compute corrections for air density, elevation, and Earth's rotation. The Coriolis effect nudges long shots slightly right in the northern hemisphere and left in the southern, a small deflection that becomes important when distances stretch. Tides reveal gravity's reach with finer tools. The Moon pulls more strongly on the near ocean than on the far, stretching Earth's water into two broad bulges. As the planet turns, coasts move through these bulges and record high and low waters with dependable rhythm. When sun and moon align, their pulls add and tides run high. At right angles, they partly cancel and tides run modest. Friction between shifting water and the seafloor converts a little rotational energy into heat and lengthens Earth's day by milliseconds per century. The Moon drifts away by centimeters each year as a result. Laser pulses bounced from mirrors left by Apollo missions' time that drift within millimeters, turning light into a tape measure and tides into a ledger. Escape belongs to the same family. On Earth, about 11 kilometers per second is the speed required to leave forever, neglecting air. Rockets do not leap to that figure at once. They climb along guided arcs, spending thrust to trade fuel mass for speed, while gravity and drag take their taxes. The numbers are unforgiving yet stable. A launch window is a polite appointment with these rates and directions, not a forceful demand. Miss the window and gravity answers with the same calm pull it had yesterday. Human bodies carry constant conversations with this field. Bones strengthen when loaded and thin when idle. Astronauts in microgravity lose calcium without daily countermeasures. Blood redistributes upward and changes pressure reflexes. Returning to 1G requires training and time. On the ground, simple habits, walking, lifting, climbing, and maintain tissues because they ask muscles and skeleton to answer a steady request. Gravity is not loud, but it is persistent enough to shape us. Even falling air obeys. Warm parcels rise because they are less dense. Cooling makes them sink. Convection cells transport heat upward and return cooler air downward, powering clouds and storms. A thunderhead is gravity working with buoyancy and latent heat in repeating loops, lifting vapor to where it condenses, releasing energy, and driving the cycle again. The same principle moves magma in the mantle slowly, and seawater in overturning currents more quickly. Downward pull and density differences organize the planet's long breaths. As the tide of thought turns, a small comfort appears. The figures are practical: 9.8 meters per second squared, 90-minute orbits, centimeters of lunar drift each year. They do not press, they guide. A child drops a stone and learns the feel of acceleration. A pilot trims approach and trusts the same curve. A tide table matches a harbor's patience to the moon's. The rule under everything is simple, and it repeats without scolding. Gravity does not hurry you, it keeps you. Thin frost glows on a quiet field, each blade holding a small arc of light. Gravity draws those arcs, but through geometry rather than an invisible tug. General relativity frames the rule cleanly. Mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. The straightest possible path in such a landscape is a geodesic, which may look bent when plotted on a flat page. Planes follow shortest paths over Earth as great circles, curves on a sphere that are straight in their own geometry. In the same way, planets follow near elliptical geodesics around the Sun, guided by curvature rather than pulled by strings. A geodesic is not a guess. It is the path of least space-time interval available. In weak fields and at low speeds, that rule reduces to Newton's gravity with familiar ellipses and periods. In strong fields or at high speeds, the differences emerge with clarity. The geometry itself holds what we once called a force, and objects simply trace what the geometry allows. This is why an orbiting satellite feels weightless while still circling Earth. It is in free fall, along a straightest possible line through curved space-time, meeting the ground only in thought, because the planet's surface curves away beneath it. The explanation sounds abstract, yet its predictions are concrete enough to guide machines, maps, and signals that knit daily life together. Clocks reveal curvature with quiet honesty. Raise an atomic clock by a few floors, and it ticks faster because it sits higher in gravitational potential. Lower it, and it slows. This is not a trick of machinery. It is time itself responding to space-time shape. Laboratory comparisons of modern optical clocks see the difference across small height changes, resolving time shifts over centimeters of elevation. The result is consistent with the rule that deeper in a gravitational well, proper time runs slow. GPS satellites ride higher still, where gravity is weaker, and they move swiftly. Their onboard clocks therefore gain time from altitude and lose time from speed. Both offsets are corrected, so positions on your phone remain steady. Without these adjustments, errors would grow by kilometers per day, and navigation would drift beyond usefulness. Time, position, and curvature stay bound together with quiet precision. Light also answers the shape. During a total solar eclipse in 1919, starlight passing near the Sun bent by about 1.75 arcseconds, a value predicted by Einstein's equations. The deflection is small to the eye, yet decisive on a photographic plate. More than a century later, the effect is routine in astronomy. Galaxies and clusters deflect background light into arcs and rings. This gravitational lensing magnifies distant objects and sometimes splits one source into several images that arrive at different times along separate curved routes. Those delays depend on path length and on the gravitational potential along each route. By modeling them, researchers estimate the expansion rate of the universe and weigh unseen matter within the lens. The sky becomes an instrument, and curvature turns into a measurable lens with glass made of mass. Mercury's orbit carries another signature that geometry explains. Its perihelion advances by a tiny extra amount each century beyond what Newtonian gravity predicts when accounting for planetary tugs. General relativity supplies the missing part, aligning calculation with sky and bringing the excess into agreement at roughly 43 arcseconds per century. The correction is small but crisp, exactly the kind of quiet difference that separates a good model from a complete one. Similar corrections grow near compact masses where curvature sharpens. Around a black hole, space-time becomes so steep that paths of light wrap into a photon ring at a specific radius. The Event Horizon Telescope assembled radio dishes across Earth to resolve that region in the giant galaxy M87. The resulting image showed a dark, central shadow edged by a bright, lopsided ring, a pattern that matches relativistic models of light paths near a deep gravitational well. The equivalence principle sits at the center and keeps the story simple. Locally, you cannot tell uniform acceleration from an unchanging gravitational field. A person in a sealed rising room feels heavier. A person in a freely falling room feels weightless. This principle guided the theory's construction and continues to guide tests. Experiments drop different materials in the same field and compare their acceleration. Torsion balances twist under tiny differences if they exist. Atom interferometers split and recombine matter waves to sense minute gravitational phases between paths at different heights. Satellite missions push the comparisons in quiet orbits above the atmosphere. So far, everything descends together within the limits of measurement, supporting the idea that gravity acts on all forms of mass energy in the same geometric way. Curvature also shapes how signals travel and how instruments must be calibrated. Radio waves from deep space probes bend near the Sun, delaying their arrival by a calculable amount. Engineers account for that extra time to recover precise trajectories. Time dilation near massive bodies shifts frequencies of clocks and spectral lines. A gravitational redshift, long measured with photons climbing in Earth's field, and with clocks compared across altitude. Even the notion of straightness must be adapted. On a sphere, a geodesic can meet itself, and two geodesics can both be straight while crossing at an angle. In spacetime, straightness includes time as a coordinate, so maximizing proper time along a freefall path defines the natural route. The mathematics is compact, but the message is human. Freefall is the most effortless way to move when the floor itself is tilted by mass. These results do not replace the old habits of thinking, they nest them. Newton's model remains an excellent approximation, where fields are weak and speeds are small compared with light. Bridges, planets, and pendulums obey it within tolerances relevant to construction and daily life. General relativity extends the picture to domains where precision and depth are required, from satellite networks to black hole edges. The continuity between models matters for trust. It ensures that the simpler story works where it should, and that the richer story agrees with it as a limit. The transition is smooth, not abrupt, like a road that widens without forcing a turn. Emotion returns quietly in the reliability of these curves. The same geometry that bends a distant quasar's light also keeps a flight path efficient across an ocean. The same shift in clock rate that guides a spacecraft through a planetary flyby also helps a phone find a street with calm accuracy. There is companionship in that unity. One set of rules, tested in eclipses and laboratories, carries both wonder and utility without strain. The world feels steadier when its deep structure explains small daily promises. Near stronger masses, the same logic continues without drama. Matter follows geodesics until forces other than gravity act. Light grazes a lensing cluster and becomes an arc for a moment, then continues on its long path. A star near a black hole moves along a path that reveals the central mass with each close pass, its period and precession now measured in crowded galactic centers. Observatories watch these motions and confirm that geometry, not an unseen tug, writes the script. Where curvature is sharp, the effects grow. Where curvature is mild, the day proceeds with familiar ease. All of this replaces mystery with measured grace. Gravity is not a hand, but the shape of the floor under every footstep. A floor that slopes gently near mountains of mass and flattens out between stars. Walk softly across it, and the rules hold you without noise. The frost will melt, the field will warm, and the arcs of light will fade. But the quiet geometry remains, steady enough to guide both a satellite and a sigh. If acceleration and gravity feel the same, time itself should show it. Let's watch the clocks. Time does not keep equal pace everywhere. Gravity sets a slope. The stronger the gravitational potential, the slower proper time flows compared with higher ground. This difference is not a flaw in machinery. It is built into duration itself by spacetime's curvature. Precise instruments make the point measurable instead of mystical. Lift a state-of-the-art atomic clock by a few centimeters on a quiet lab table and it will gain on its twin below. Carry the same clock to a mountain observatory, and it collects nanoseconds each day against a copy left at sea level. The numbers are tiny, but they land exactly where equations say they should. A short, supportive line. What feels like a flat road is, in truth, a gentle downhill for time. Satellites keep the arithmetic honest. The GPS constellation orbits near 20,000 kilometers, where Earth's pull is weaker and altitude speeds their clocks by roughly 45 microseconds per day. Motion pushes back a little. Orbital speed slows them by about 7 microseconds per day. Engineers program both effects into each spacecraft's timekeeping so that the net pace matches ground standards. If they didn't, positions on your phone would wander by kilometers within a single day. Pilots would steer toward runways that had slid on a map. Tractors would lay seed in crooked bands. Survey lines would drift. Instead, corrections run constantly, and every clean blue dot on a screen is a quiet confirmation that gravity bends time and that we know by how much. Astronomy reads the same slope with light. In white dwarfs, spectral lines shift to red because photons climb out of deeper potential. Sirius B, dense and pale, shows the effect clearly in its spread of wavelengths. Neutron stars go further. Their matter is compressed beyond ordinary atomic structure. A teaspoon would outweigh a mountain. Rotation periods measured at Earth are longer than the periods in a co-rotating frame, simply because time itself is slower near the prize. Star. Pairs of such objects act like metronomes for the universe. The famous binary pulsar, discovered in the 1,970 seconds, loses orbital energy at a rate that matches the predicted emission of gravitational waves. Decades of careful timing drew that curve, long before LIGO heard the first faint chirp in 2015. No drama, just patient agreement between theory and sky. Stories often race to extremes, so a fictional planet skimming a black hole becomes a theater of hours stretched into years. Real systems give gentler versions, yet the principle scales cleanly. Near the supermassive black hole at our galaxy's center, Sagittarius A*, time dilation is measurable for stars that swing in tight ellipses, especially the well-tracked S2. At safe distances, the factor is modest. Closer in, it grows. Deeper means slower, always. The same rule can be tested without leaving Earth. Fly an accurate clock, leave one behind, and compare them when they reunite. The difference is small but repeatable, and it matches the numbers that fall from Einstein's field equations when motion and gravity are both included. Laboratories now pull the curve into sharper focus. Optical lattice clocks built from strontium or ytterbium atoms reach fractional uncertainties near 1 part in 10 to the 18th. They hold atoms in grids of light, so motion is minimized, and quantum transitions can be counted like beads. With that fidelity, a clock senses a change in tick rate when it is raised by centimeters because the gravitational potential has shifted. Metrology turns this sensitivity outward and gives it a name: chronometric geodesy. Instead of hauling a level across rough ground, a network of clocks can map tiny variations in gravity that reveal density underground. The idea extends naturally to hazards. A volcano filling with magma slightly changes the local potential. A hillside packed with water after rain does the same. Arrays of clocks could, in time, add an independent layer of awareness to seismic and satellite tools, not replacing them but smoothing their gaps. Spectroscopy adds another thread to the same fabric. Near the limb of the sun, light also climbs out of a well, and high-precision measurements see a small shift consistent with gravitational redshift plus the sun's motions. In the lab, Pound and Rebke measured a related effect in 1959 by sending gamma rays up a tower and reading the tiny energy change required to keep absorption resonant against gravity's pull. Those careful floors and ceiling experiments capture the same slope that GPS corrects and that pulsars whisper across light years. The scale changes, the rule does not. Practical life relies on synchronized compromise between many local nows. Financial networks timestamp trades to microseconds, so order and fairness hold under pressure. Particle accelerators choreograph bunches of charges to billionths of a second, so collisions meet cleanly at the heart of a detector. Radio dishes separated by continents record the same quasar with clocks so steady that their data can be combined into a mirror the size of Earth. Very long baseline interferometry only works because every station knows exactly how its seconds compare with every other station's seconds after gravity and motion are accounted for. Even a photograph of a black hole's shadow depends on that quiet agreement. Without shared time, the image would unravel into noise. The human thread enters softly and stays modest. Gravitational dilation does not offer practical youth. The differences across a life on Earth are far smaller than a blink. Yet these slopes remind us that present tense is local, negotiated, and maintained. Your watch keeps pace with the street, the aircraft keeps pace with its lane of sky, and a satellite keeps pace with a ring of empty cold that sits a quarter of the way to geostationary orbit. Synchronization is work. It is also a kindness we extend to one another so that trains meet platforms and nurses, meet rounds and friends meet at doors at an agreed hour. Time, bent by gravity, still becomes community through intention. As the green ribbon over the pole fades, the lesson remains steady. Clocks change, speed with height. Light loses energy climbing out of wells. Orbits confess their drains in slow spirals. Equations, devices, and stars speak the same sentence in different dialects. And the sentence says that duration leans downhill where mass is gathered. Let that be a comfort rather than a worry. The slope is shallow enough to trust the day and clear enough to measure the night. And in that balance, the world keeps its appointments with quiet ease. Mist lifts from a sleeping shoreline. The tide returns without hurry. Far beneath that hush, another ocean moves, and in 2015 its swell passed straight through Earth. Gravitational waves are traveling distortions of space-time. As a crest goes by, distances stretch in one direction and shrink in the perpendicular, then reverse with the trough. The effect is incredibly small, but it is real and predictable. Laser interferometers measure it by comparing the lengths of two long, perpendicular arms. If a wave changes those lengths differently, the returning laser beams recombine out of step and leave a faint signature in light. LIGO built two such instruments, each with 4-kilometer vacuum arms, one in Washington and one in Louisiana. Their mirrors hang from multi-stage pendulums that isolate them from ground shake, wind, and passing trucks. On the 14th of September 2015, a short, rising chirp appeared almost simultaneously in both detectors. The signal's frequency swept upward in less than half a second, just as theory predicts for two black holes spiraling together and merging. The amplitude swelled as the pair approached and radiated more energy. After union, the new single black hole rang down, and the wave faded. The arrival times at the two sites differed by about 7 milliseconds, enough to sketch a rough direction on the sky. Modeling showed component masses a few dozen times the Sun and a source more than 1 billion light-years away. General relativity had forecast such waves a century earlier. Now the pattern sat cleanly in the data. Detection did not end with that first event. The upgraded LIGO instruments, joined by Virgo in Europe and later Kagra in Japan, have observed dozens more mergers. Many involve stellar mass black holes, some heavier than expected from earlier surveys. Others include neutron stars, the dense remnants of massive stars that collapsed but did not form black holes. In 2017, 2 neutron stars spiraled together and produced a signal, long enough to trace thousands of orbits. Roughly 2 seconds after the gravitational wave's peak, a short gamma-ray burst arrived from the same region of sky, followed by an optical and infrared glow that evolved over days. That kilonova light carried the fingerprints of rapid neutron capture, the R process that builds heavy elements like gold and europium. The near-simultaneous arrivals cemented that neutron star mergers can forge precious metals and tied the speed of gravitational waves to the speed of light within tight bounds. These instruments extract physical parameters from the waveforms because general relativity dictates the shapes. Mass sets the clock rate of the in-spiral, spin twists the phase, distance and orientation scale the amplitude. Analysts generate vast banks of theoretical templates and match them to the data, inferring not only what merged, but how fast it spun and how far its tremor traveled. The method works because the sources are simple in a strict sense, compact, relativistic, and governed by well-tested equations. Where gravity is strongest, the theory is clearest, and the waves carry that clarity to us. Noise is an unavoidable companion. Quantum fluctuations in the laser light introduce shot noise, blurring the measurement at high frequencies. Engineers reduce it with squeezed states of light that trade uncertainty in one optical quadrature for lower noise in the other. Thermal agitation in mirror coatings adds jitter. Materials scientists develop low-loss glasses and crystalline coatings to quiet it. Seismic motion dominates at low frequencies. Multi-stage suspensions and active isolation push the ground's restlessness away from the mirrors. Stray lines from power grids, pumps, and electronics require careful subtraction. Even with these controls, data streams must be vetoed for storms and local disturbances. Yet the signals still rise above the floor because their forms are exact and their coincidences across observatories are unlikely to be chance. Localization improves when more detectors listen. With 3 or 4 instruments online, time delays between sites pin down source regions far better than 2 can. That precision lets telescopes catch afterglows quickly, building full stories from radio to gamma rays. Multi-messenger astronomy light plus gravitational waves turns a single event into a laboratory. It checks nuclear physics in neutron star matter, measures the geometry of space-time, and refines estimates of the universe's expansion rate by treating each merger as a standard siren. The distance comes from the wave's amplitude. A redshift from light, when available, pairs with it. Each pair adds a point to the cosmic map. Planned instruments widen the band. A space-based observatory, LISA, will fly 3 spacecraft in a triangle trailing Earth, with arms millions of kilometers long linked by lasers. Its sensitivity will sit in the millihertz range, well below LIGO's band. Supermassive black hole binaries in distant galaxies will sweep through that range months to years before merger, giving long, clean signals. Compact binaries of white dwarfs in our own galaxy will provide a steady background and individual resolvable sources. On Earth, next-generation facilities, such as the Einstein Telescope in Europe and Cosmic Explorer in the United States, aim for longer arms and quieter sites, pushing reach to earlier cosmic times and lighter sources. An even slower rhythm is probed by pulsar timing arrays. Millisecond pulsars are natural clocks, spinning hundreds of times per second and beaming radio pulses with remarkable regularity. A passing nanohertz gravitational wave slightly advances or delays those pulses along certain directions in the sky. By monitoring many pulsars across the galaxy for years, collaborations can detect a correlated quadrupolar pattern that signals a gravitational wave background, likely from cosmic populations of supermassive black hole pairs. Recent reports from multiple arrays show consistent hints of such a hum, the earliest common music of merging giants spread over the distant universe. The emotional truth here is patience rewarded. The signals are faint, but they are faithful, and they arrive carrying precise stories from places no light can escape. Each detection is a conversation with strong gravity rather than a guess about it. The technology is demanding, yet it serves ordinary ends: clear knowledge, shared standards, and a better map of where we live in time. A short, supportive picture helps. Think of space-time as a calm drum. When massive bodies collide, the membrane rings, and careful microphones hear the tone. Practical benefits emerge alongside wonder: calibration upgrades, vacuum engineering, vibration control, and quantum optical techniques ripple into other fields. The global network trains specialists who carry these skills to medicine, geoscience, and communication systems. Data sharing builds habits that improve reliability across projects. Even the simple fact that 2 detectors hear the same wave within milliseconds ties continents together with physics rather than schedule. As the night deepens, the takeaway stays soft and steady. Gravitational waves fulfill an early prediction and open a new sense for astronomy. They let us witness black holes and neutron stars by the geometry they disturb, not by the light they cast. They travel essentially unscattered, preserving the shape of distant violence with exquisite fidelity. With patient instruments, we can listen, and with each new tone, the dark becomes more familiar. Another quiet swell crosses the planet, and the long arms breathe in step, measuring a universe that moves and remembers. Sea fog lifts from a gray inlet, leaving polished water and precise ripples. Tides are gravity's handwriting on the ocean, composed by differences across Earth's diameter. The moon's pull is stronger on the near side than on the far side, raising 2 broad bulges that travel with the Earth-Moon system while coastlines rotate through them. Many shores feel 2 highs and 2 lows, each lunar day of roughly 24 hours 50 minutes. Some, shaped by bays and shelves, meet a single rise and fall. Others mix the pattern into one larger and one smaller pair. The sun adds a second line of influence. When sun, earth, and moon align at new and full moon, spring tides climb higher. At first and third quarter, neap tides settle low. These rhythms are calculable because the motions and masses are known, and because the sea responds with a patience that can be tabulated for years ahead. The bulges do not point exactly at the moon. Earth spins faster than the moon orbits, and friction along coasts and seafloors carries the bulges slightly forward of the line between centers. That small lead becomes a torque. Angular momentum leaks from Earth's rotation into the moon's orbit. Days lengthen by fractions of a millisecond per century. A quiet drift you will not feel, yet one that observatories record. The moon recedes by about 3.8 centimeters each year. Laser pulses sent from Earth to retroreflectors, left by Apollo missions time, that round trip to billionths of a second, and confirm the recession cleanly. Deep time carries the same signature. Certain fossil corals and tidal rhythmites preserve daily bands. Counted back into the Devonian, they imply over 400 short days per year. Rocks, shells, and lasers agree. The tide trades spin for distance and keeps careful books. Not all tides march straight to shore. In many ocean basins, waves swirl around, amphidromic points, quiet centers where the tidal range nearly vanishes, and phase rotates like the hand of a clock around a hub. Basin, geometry, Coriolis deflection from Earth's rotation, and resonance set these whirls. Narrow straits can amplify flow into standing waves, while broad shelves can delay peaks by hours. Local detail explains why one harbor breathes gently and another races like a river on the turn, where the seabed is complex. Predictions include many harmonics, each tied to a known orbital term. The superposition builds a forecast, and mariners trust it to pass through narrows, dock heavy hulls, and time a safe bar crossing. Tidal work is not only surface motion, it moves energy through crust and mantle. The same differential pull that lifts oceans needs worlds. Jupiter's gravity flexes Io, keeping rock warm enough to erupt in fountains and feed a thin atmosphere with sulfur. Europa and Enceladus hide global oceans beneath ice. Tides stir them and may help deliver heat and minerals to seafloor vents. Even our moon shows long scars of early heating when orbits were tighter and the tug stronger. Closer to home, the tidal torque shapes spin states. The moon rotates once per orbit and keeps one face turned toward us, a synchronous lock reached as internal friction bled away rotation. Mercury fell into a 3-to-2 spin-orbit resonance, rotating 3 times every 2 orbits because its path is more elliptical and solar tides grip unevenly along the track. Locks and resonances are not myths. They are the resting points of systems that have paid off their wobble with heat. Orbits themselves are the quiet solutions to gravity's geometry. Planets follow ellipses with the sun at one focus and sweep equal areas in equal times. The square of the period scales with the cube of the semi-major axis. Newton showed these relations fall out of an inverse square pull. General relativity adds tiny corrections, such as Mercury's extra precession, which match observation to arc seconds per century. People extend these curves with machines. Low Earth orbits carry satellites in about 90 minutes and feel drag that slowly lowers altitude. Geostationary orbits sit near 35,786 kilometers above the equator and circle once each sidereal day, appearing fixed to ground dishes. A Hohmann transfer between circular paths uses 2 short burns and patient coasting to save propellant. Gravity assists around planets' trade, speed, and direction for free, bending paths the way a skater takes a hand to whip around a partner. Missions stitch these moves together to reach distant targets with modest fuel. Spin couples to gravity and shape and leaves its own marks. Earth is not a perfect sphere. Rotation lifts an equatorial bulge. Gravity from sun and moon pull on that bulge and make the axis precess like a slow top over roughly 26,000 years. The celestial pole wand. Gravity can be measured, not only felt. In 1798, Henry Cavendish used a torsion balance to weigh the Earth by detecting the tiny attraction between lead spheres. A thin fiber twisted when masses drew together. From the twist, he inferred the gravitational constant, g. That constant sets the strength of gravity in Newton's equation and remains one of the least precisely known of the fundamental numbers. Modern experiments refine Cavendish's idea with vacuum chambers, laser readouts, and careful temperature control. Yet published values for g still differ more than expected. The problem is simple to state and hard to defeat. The signal is minuscule, while the world is restless. Seismic murmurs pass through floors. Air moves with doors and weather. Even a researcher's warmth can create a whisper of convection that pushes on a pendulum. So experimenters subtract, shield, suspend, and wait, treating quiet like a material they can shape. Absolute gravimeters follow a cleaner line. They drop a small corner cube mirror in a vacuum and time its free fall with lasers to astonishing precision, often parts per billion in g. The geometry is spare. Distance, time, acceleration. A vacuum removes drag. A frequency-counted laser removes guesswork. Superconducting gravimeters take another route. They levitate a niobium sphere in a magnetic field and hold it as still as a thought. When local gravity changes by a few microgals, 10 billionths of Earth's gravity, the sphere's position shifts by less than an atom's width. The instrument hears the planet breathe. Daily ocean tides flex crust and mantle. Distant storms load the atmosphere. Slow post-quake adjustments lift basins by millimeters. Each change carries mass, and mass changes gravity. The record looks like a gentle song written in seconds. In orbit, the listening widens. Twin satellites named Grace, and later Grace Foe, chase one another along nearly polar paths. Where Earth's gravity is slightly stronger, the leading craft is tugged ahead. The trailing one catches up. Where it is weaker, they drift apart. Microwaves and now lasers measure the separation to micrometers across hundreds of kilometers. Month by month, maps emerge of mass moving on and under the surface. Greenland's ice thins from the edges inward. Snowpacks grow and melt across seasons. Aquifers in dry plains fall when pumping exceeds recharge. After a great earthquake, mass shifts sideways and down, and the gravity field records the rearrangement like a fingerprint. The satellites have no cameras for these changes. Gravity itself provides the picture. Closer to the ground, relative gravimeters walk grids across fields and streets. Engineers look for voids beneath planned foundations, places where concrete would sag if poured. Archaeologists pace old plazas and draw outlines of buried walls and courtyards without breaking a single stone. In limestone country, surveyors read faint lows that hint at hidden chambers and fragile roofs. Each reading takes minutes. Drift must be corrected. The meter returns to a base point again and again, as patient as a surveyor's heartbeat. The unit they speak is tiny, a gal for Galileo, and often a microgal for the variations of interest. For most work, a few dozen microgals matter. For the most delicate, a few. Quantum tools have entered the room softly. Atom interferometers cool clouds of rubidium or cesium to a crawl, then split and recombine their matter waves with a sequence of laser pulses as the atoms fall. The phase difference between the two paths reveals G with exceptional stability. Because the atoms themselves are the test masses and the laser pulses define rulers and clocks, many common disturbances cancel. Arrays of these instruments are being tested near restless volcanoes. A slow, steady rise in gravity can mean denser magma is moving upward. A sudden drop can mean voids are opening as fluids migrate. Early warnings may arrive as a line on a quiet screen long before steam or tremor announces itself. All of this measurement ties back to shape. Earth is not a perfect sphere. It bulges slightly at the equator and flattens at the poles. More subtly, mountains, trenches, and mantle currents make the gravity field lumpy. The surface that would be reached by still oceans and equipotential snakes up and down relative to mean sea level by tens of meters. That surface is the geoid, and modern height systems tie themselves to it rather than to a single tide gauge in a single harbor. A pipeline crossing a continent now references one continuous surface, not a patchwork of local seas. Navigation, flood models, and drainage plans stay consistent because the zero is meaningful everywhere. Time adds a new ruler to the kit. According to relativity, clocks lower in a gravity well tick more slowly than clocks higher up. For ordinary heights, the difference is tiny, but modern optical clocks see it. Lift a clock by a hand's breadth, and its frequency shifts by a measurable part in quadrillions. Chronometric geodesy compares ultra-precise clocks at different elevations and turns those shifts into a map of gravitational potential directly. Where gravity is higher, time is slower. The difference becomes a measure of height. In the lab, this feels like magic made from patience. In the field, it promises new ways to watch subsidence in delta cities, to track groundwater returning after rains, to see a mountain lighten as a glacier thins. One short image helps. We weigh hills by listening to seconds. To make any of these signals trustworthy, noise must be named. Earth tides stretch crust by centimeters every day and must be modeled and removed. Atmospheric pressure loads the ground and changes gravity by microgoules. Barometers feed corrections into the record. Polar motion and ocean loading add their own periodic signatures. Even the instrument's thermal drift needs taming with long runs and returns to base points. The methods vary, but the posture is constant. Attend, subtract, repeat, and let the small remainder speak. The reward is practical. A tunnel can be routed away from hidden caverns. A reservoir can be managed knowing the aquifer's mass in real time. A glacier's loss can be monitored through winter cloud and summer sun with equal care. The human feeling inside these facts is companionship with a steady partner. Gravity does not shout, it leans. It changes when water moves, when rock warms, when ice lets go, when plates breathe after strain. Instruments built with patience can hear those changes and translate them into choices on the ground. A farmer sees a season's drawdown and trusts the number. A coastal planner reads long trends and regrades a road. A scientist watches a volcano's slow inhale and moves sensors upslope. The same constant that Cavendish teased from a twisting fiber now guides satellites and wells and quiet rooms that count atoms by the beat of light. As the tide of thought turns, the bench grows still again, and the lantern's tremble settles. Gravity remains what it always was, a soft pull that can be named, mapped, and trusted. A thin dust plume lifts from a quiet disk and hangs above a young star. Grains turn in pale lanes, and the circle keeps its hush. Gravity begins its work by gathering what is small. In a protoplanetary disk, micron-sized particles collide gently and stick through electrostatic forces. As aggregates grow to millimeter and centimeter sizes, gas drag matters. Pebbles drift inward because the gas orbits slightly slower than Keplerian speed. Concentrations form where pressure is higher and drift slows. In those bands and eddies, solid to gas ratios rise until the streaming instability takes hold. pulling pebbles together into dense filaments that feel their own self-gravity. Clumps collapse into kilometer-scale planetesimals quickly, turning dust lanes into building blocks that can endure collisions rather than crumble. Once planetesimals exist, growth accelerates. Gravity focuses their encounters, increasing impact cross-sections beyond their simple areas. Merging bodies release heat. Interiors can partially melt if the objects are large and rich in aluminum-26, a short-lived radionuclide that warms young rock. Molten regions allow iron to separate and form cores, while lighter silicates rise, creating layered worlds in miniature. In the colder outer disk, water, ice, and other volatiles join rock, raising the solid mass available so cores of 10 Earth masses can assemble rapidly. Those cores attract hydrogen and helium, while gas still fills the disk, inflating into giant planets before the nebula dissipates in a few million years. The map does not stay still while this happens. Embedded planets exchange angular momentum with the surrounding gas and migrate. Low-mass planets feel spiral density waves and drift inward or outward, depending on local gradients, a process called type I migration. Massive planets open partial or full gaps and move with the disk's viscous flow in type II migration. These quiet trades in momentum help explain hot Jupiters found skimming their prams, stars, as well as resonant chains where neighboring planets lock into simple period ratios. The TRAPPIST-1 system shows 7 small worlds in near resonances. Their spacing hints at migration and gentle capture, while the gas still lay thick. When the nebula thins and leaves behind planetesimals, scattering continues the rearrangement. Icy bodies deliver water and carbon compounds inward. Giant impacts finish assembly. The leading explanation for our moon's origin is a collision between the young Earth and a Mars-sized protoplanet. The impact's debris gathered into a companion with angular momentum and isotopic fingerprints that match what the rocks carry. When the dust clears, orbits settle into patterns shaped by mass and distance. Kepler's laws hold with quiet accuracy. Planets sweep equal areas in equal times, and the square of a period scales with the cube of the semi-major axis. Mutual perturbations add small precessions and resonances that accumulate slowly. Jupiter's mass dominates many of these structures. Its 2-to-1 and 3-to-1 mean motion resonances carve gaps in the main asteroid belt, and stable regions 60 degrees ahead of and behind Jupiter's orbit. Lagrange points L4 and L5 host Trojan swarms that circle with the planet. Around Saturn, resonant tugs maintain architecture at a finer scale. Mimas helps define the Cassini division. Small shepherd moons such as Prometheus and Pandora confine the sharp edges of the F-ring, keeping particles in a narrow strand through repeated nudges. Where multiple resonances overlap, motion becomes chaotic. Small changes in initial conditions grow over long spans, a sensitivity that matters to stability across millions of years, but rarely touches human schedules. Fine dust cannot linger forever. Sunlight exerts radiation pressure that slightly offsets gravity for tiny grains, while Poynting-Robertson drag robs orbiting particles of a trace of angular momentum and makes them spiral slowly inward as they re-radiate. Energy. Micrometeoroid impacts grind larger fragments into replenishing powder, and moonlets shed material when tides and collisions loosen their surfaces. The balance keeps rings bright and zodiacal light present, even as individual grains are transient. Comets show gravity's reach into the dark. Beyond Neptune, the Kuiper belt stores icy bodies on relatively flat, sun-distant paths. Farther out, the Oort cloud likely surrounds the solar system as a spherical reservoir stretching tens of thousands of astronomical units. Passing stars and the galaxy's tidal field perturb those remote orbits, sending long-period comets inward on million-year schedules. Near the Sun, solar heating releases gas and dust to form comae and tails that always point away from the Sun, yet the orbits themselves obey simple ellipses and parabolas. Impacts from such bodies, though sparse in recent epochs, have reset ecosystems. The Chicxulub crater records an event 66 million years ago linked to the end of many Cretaceous lineages. On airless worlds, crater counts offer a clock. Surfaces with more craters are older, and patterns allow relative dating where samples are scarce. Elsewhere, the same rules repeat with new arrangements. Thousands of exoplanets found by transit dips and stellar wobble reveal that super-Earths and mini-Neptunes are common sizes that our system lacks. Many pack closely within orbits shorter than Mercury's year, suggesting that migration and disk conditions favored compact families. Some systems hold resonant chains that imply smooth histories. Others show tilted or elongated orbits that point to later scattering or Kozai-Lidov cycles with distant companions. Direct images have captured a few giant planets still warm from formation, circling young stars at tens of astronomical units, the glow of their contraction betraying their youth. Together, these observations show that gravity supplies the frame, while chemistry, temperature, and starlight write the team. Details. The feelings these facts invite are patience and companionship. Worlds are not thrown together. They are assembled by steady processes that carry on without applause. A pebble drifting inward because gas orbits a little slow is a quiet step toward a continent and an ocean. A captured resonance that keeps two planets in rhythm is a small safeguard against near collisions. Even the rare violence of a giant impact falls within rules that allow a moon to coalesce and tides to begin. What seems sudden in a diagram is measured in thousands, then millions, then hundreds of millions of years, long enough for atmospheres to thicken and for surfaces to cool and crack into plates. As the scene dims in the mind, the thin plume still circles the star, and the disk continues its simple arithmetic. Mass gathers, orbits trade momentum, heat flows outward and leaves structure behind. When the gas finally clears, patterns remain that last for ages. Rings with edges held by shepherds, belts shaped by giants, families of planets that keep their appointments by Kepler's plain law. The lesson stays gentle. Where material collects, gravity makes and moves worlds, and the arrangements endure long after the fog has gone. A faint river of starlight threads between clustered galaxies, thin and cold. Gravity reveals more than our eyes allow. In spiral systems, stars far from the center orbit, too fast for the visible mass to hold them. Plot the speed against radius, and the line stays flat instead of falling. Gas clouds share the pace. The implication is steady. An unseen halo dominates the mass, extending well beyond the luminous disk. Radio maps of hydrogen trace those outer reaches for hundreds of thousands of light-years and keep the curve level. The story repeats across many spirals, large and small, with numbers that differ, yet patterns that agree. In galaxy clusters, the signal strengthens. Galaxies move within a shared well, as if something massive binds them, far more than the light from stars and gas can explain. X-ray telescopes find hot plasma filling the space between members. That gas is tens of millions of degrees and should drift away unless the gravitational pit is deep. It stays because the mass is large. Lensing adds a third line of evidence. Light from background galaxies, arcs, splits, or subtly shears as it crosses the cluster's potential. From those distortions, astronomers reconstruct a smooth, heavy halo that outweighs the total brightness by comfortable factors. 3 methods, motions, hot gas, and bent light, point to the same calm conclusion. Dwarf galaxies underline the case with quiet emphasis. Some contain very few stars, yet their internal speeds remain higher than luminous matter can support. Mass-to-light ratios climb toward triple digits. The simplest reading is that dwarfs live inside dominant dark halos. Tidal streams around our own galaxy add constraints. When a small system is pulled apart, its stars stretch into long ribbons. The shapes and wiggles of those streams respond to the Milky Way's dark matter distribution. Surveys use that response to map clumps and smoothness, finding a halo that is extended and mostly collisionless, with people to time. Substructure on modest scales. The bullet cluster brings a striking snapshot. 2 clusters have passed through each other. Their hot gas, visible in X-rays, collided and lagged. But the mass mapped by gravitational lensing lies ahead, centered on the galaxies that sailed through with little resistance. The separation between gas and mass matches the expectation for dark matter that barely interacts, except through gravity. Other merging systems show similar offsets. Each one is not a decisive verdict alone, but together they build a coherent picture in which the invisible component behaves as a near collisionless fluid. Candidates for this component remain open but bounded. Weakly interacting massive particles once led many models. Ultralight axions offer a contrasting possibility with wave-like behavior on galactic scales. Compact faint objects, macos such as brown dwarfs or primordial black holes, were tested with microlensing and background light. They cannot account for the bulk without violating those constraints. Deep underground, detectors sit beneath mountains or kilometers of rock, shielded from cosmic rays, waiting for a rare interaction between a passing particle and a nucleus. Noble liquid targets count single flashes. Cryogenic crystals listen for minute heat. So far, the instruments have set limits rather than found signals, and parameter space has narrowed. That absence does not dismiss dark matter. It guides designs toward quieter corners where new particles could live. On the largest scales, the role of dark matter is architectural. Tiny density ripples in the early universe, written in the cosmic microwave background, grew under gravity. Because dark matter does not feel radiation pressure, it began clumping earlier than ordinary gas could. Those clumps pulled baryons inward after the universe cooled enough for atoms to form. Supercomputer simulations, seeded with the measured ripples and the observed matter mix, evolve into a cosmic web. Filaments, nodes, and voids, whose statistics match sky surveys. Galaxies assemble along the threads. They merge at nodes and accrete gas from strands, while feedback from supernovae and black hole outflows sculpts the luminous parts without erasing the underlying scaffold. Alternative gravities have been proposed to fit galaxy rotation with modified laws at low accelerations. They often match the flat curves in spirals by adjusting the rule rather than adding mass. Yet these schemes struggle where independent probes converge. Clusters require more binding than the modified law alone can supply. Lensing in systems like the bullet cluster locates mass where light is scarce. The detailed pattern of peaks and troughs in the microwave background points to non-baryonic matter present in the first few 100,000 years. A single tune can fit one instrument. A symphony needs harmony across all sections. Current surveys keep tightening the frame. Weak lensing maps from wide fields measure tiny shape changes in millions of galaxies and build mass maps without relying on starlight. Stellar streams, traced by precise positions and velocities, reveal lumps in the halo that could be dark subhalos without stars. Pulsar timing arrays search for subtle tugs that could betray compact dark objects. Even within galaxies, the thickness of gas disks and the flaring of outer layers carry information about the halo's depth and shape. Each method is modest alone. Together they lean in the same direction, a dominant, transparent component, gently binding what shines. The numbers that emerge are simple to carry. In the standard picture, dark matter accounts for most of the matter in the universe and outweighs ordinary atoms by roughly 5-to-1. It makes up about a quarter of the total cosmic energy budget, with dark energy filling most of the rest. Those proportions, pulled from background radiation, galaxy clustering, and supernova distances, have held steady as data improved. They, to leave detailed questions alive: particle identity, distribution, on the smallest scales yet hold the large canvas stable. Feeling enters through the reliability of that quiet support. Dark matter does not touch the skin or flavor the air. It does not complicate a meal or a map. It simply steadies the stage. The Milky Way's stars, including the Sun, orbit within a broad halo that keeps the disk intact against the tug of neighbors and the slow pull of expansion. A short metaphor may help and then rest. The luminous galaxy is a lantern, and the dark halo is the unseen handle that lets it be carried without spilling its light, then return to fact. The handle's weight is measured by rotation, by lensing, by the pressure of hot gas, by the dance of dwarfs. As the evening deepens, the mystery feels patient rather than alarming. The absence of a direct particle signal is not a failure. It is a boundary that improves design. The agreement among independent astrophysical clues is not an accident. It is a pattern that invites trust. What we do not yet name still performs a steady task: seeding structure, holding families of stars together, and etching the grand web across which galaxies travel. Black holes are places where escape would require faster-than-light speed. The event horizon marks the boundary where outward paths still exist locally, but all future-directed routes lead inward overall. For a non-rotating Schwarzschild hole, the horizon radius scales cleanly with mass, about 3 kilometers per solar mass, so a 10 solar mass remnant spans roughly 30 kilometers, while a 4 million solar mass object, like the one at the Milky Way's center, spans about 12 million kilometers. Rotation changes the picture. A Kerr black hole drags space-time around with it. Outside the horizon lies the ergosphere, a region where no object can remain at rest relative to distant stars. Within classical theory, world lines end at a singularity where curvature diverges and known physics breaks down, signaling that a quantum description is still missing. From a distance, black holes are strikingly simple. They are characterized by only mass, spin, and charge. Astrophysical environments neutralize charge efficiently, so observations mainly measure mass and spin. Those two parameters govern the size of the horizon, the location of the innermost stable circular orbit, and the energy available to power disks and jets. Gas drawn inward forms a hot accretion flow. Friction and magnetic turbulence heat it to tens of millions of degrees, producing X-rays and ultraviolet light. Magnetic fields, anchored in the swirling plasma, can collimate twin relativistic jets along the spin axis, visible across millions of light-years at radio and X-ray wavelengths. In close binaries, a black hole can siphon gas from a companion. The inflow thickens into a disk whose inner edge flickers on millisecond to second timescales, matching orbital periods expected near the last stable orbits for stellar mass holes. Supermassive black holes settle in galactic centers. Sagittarius A times in our own galaxy weighs about 4 million suns. Infrared observations track individual stars most famously. S2 racing along elongated orbits that carry them within light hours of the center. At pericenter, S2's spectral lines showed gravitational redshift and a relativistic precession, consistent with general relativity's predictions. In other galaxies, masses reach millions to billions of suns. The black hole in M87 anchors a jet that extends thousands of light-years. Its central mass is near 6.5 billion suns, inferred from gas dynamics and stellar motions near the core. Light near a black hole maps geometry with exquisite honesty. Photons at a special radius can orbit repeatedly. Slight nudges send them inward or outward, producing a bright, narrow photon ring surrounding a darker interior, often called the shadow. The Event Horizon Telescope, a global array using very long baseline interferometry, resolved an asymmetric ring around M 87 times and a blurred crescent around Sagittarius A*. The sizes matched predictions for their measured masses and distances. The asymmetry arose from relativistic beaming in the rapidly moving plasma on the approaching side of the disk. Variability timescales in the images and light curves align with orbital periods near the innermost stable circular orbit, shorter for smaller holes and longer for giants. Polarization maps revealed ordered magnetic fields threading the plasma, indicating that magnetized flows help launch and collimate jets from the inner regions. Mergers broadcast their presence through gravitational waves. The LIGO and Virgo detectors record characteristic chirps as black hole pairs spiral inward, coalesce, and settle as a single remnant. The waveforms encode the component masses, their spins, and the final object's spin. After merger, the remnant rings in quasi-normal modes, whose frequencies and damping times depend only on mass and spin, a concise test of the no-hair property. So far, the spectra match general relativity within uncertainties. Some events show spins misaligned with the orbital plane, suggesting dynamical assembly in dense clusters rather than the slow evolution of isolated stellar binaries. Detection rates, mass distributions, and spin orientations now inform models of stellar evolution, supernova outcomes, and cluster dynamics across galaxies. Even without mergers, space-time near black holes influences passing light. Strong gravitational lensing can form multiple images and Einstein rings around foreground masses. Near a horizon, the lensing is so extreme that light skimming the edge contributes to the photon ring structure. Time delays between lensed paths through galaxy clusters let astronomers measure cosmic expansion history. While those lenses are not black holes, the same mathematics describes how curvature bends light. Close to a hole, the curvature becomes steep enough that even rays aimed outward can loop back, shaping the observed shadow. Hawking's calculation added a quantum footnote with large consequences. Black holes should emit a faint thermal spectrum, losing mass over time. For a stellar mass hole, the temperature is tiny, and the evaporation time exceeds the age of the universe by an overwhelming margin. Only hypothetical primordial black holes with asteroid-scale masses would evaporate measurably today, but no confirmed signals exist. The idea remains important because it connects gravity, quantum fields, and thermodynamics in one relation, assigning black holes an entropy proportional to horizon area and a temperature set by surface gravity. Those links hint that space-time itself may have microscopic degrees of freedom still unknown. Tides explain why proximity matters. Although replacing the Sun with a one solar mass black hole would leave planetary orbits essentially unchanged, approach to any compact object amplifies gradients. The difference in gravity between a head and feet, or between the near and far sides of a spacecraft, grows rapidly as distance shrinks. Within a critical radius, tidal forces can stretch and disrupt objects, a process dramatized in popular accounts as spaghettification. In realistic scenarios, disruption occurs well outside stellar mass horizons for fragile bodies, while supermassive holes can allow stars to pass surprisingly close before tidal limits are exceeded. Debris from disrupted stars can briefly feed brilliant flares as it spirals inward and heats. Measurement continues to refine the simple portrait. X-ray spectra from accretion disks carry broadened iron lines whose skewed shapes reflect Doppler shifts and gravitational redshift near the inner edge. Modeling those lines constrains spin because the innermost stable orbit moves inward as spin increases. Radio and millimeter observations trace jet bases and reveal how power scales with mass accretion rate and magnetic flux. Pulsar timing arrays now report low-frequency gravitational wave backgrounds, likely produced by the slow dance of supermassive black hole binaries across the universe, a deep baseline beneath the higher frequency chirps detected by ground-based interferometers. The emotional cadence here is restraint. Black holes do not hunt. They obey geometry. They curve space-time according to mass and spin, and respond to what falls within reach. The rules are austere and dependable. Orbits precess by set amounts, light reddens by predictable fractions, and waves ring with specific notes. The single idea gravity as geometry accounts for the bright disks, the narrow rings, the jets that stitch galaxies, and the ripples that tug mirrors on Earth by less than a proton's width. As the ridge cools and the valley keeps its quiet, the comfort is this: the darkest objects are also among the most knowable, and their steady mathematics lets wonder rest without fear. Running produces genuine foot strikes. Cycling ergometers sustain cardiac output and leg endurance. Some programs add lower body negative pressure to draw blood toward the feet, retraining baroflexes for standing on landing day. Nutritional plans emphasize adequate protein, calcium, and vitamin D. Sodium is managed to avoid excessive fluid shifts. Bisphosphonates and other bone-active agents have been tested to slow resorption. Training intensity matters. Shorter, vigorous sessions often preserve capacity better than long, easy ones in constrained schedules. Sleep and daily timing drift when the horizon vanishes. In low Earth orbit, the station circles the planet about 16 times a day, producing many sunrises that would scramble circadian phase. With OA dim, hospital corridor hums softly. Monitors tick with steady patience. Gravity shapes physiology as much as orbits. On Earth, fluids tend to settle toward the legs, so stretch-sensitive baroreceptors in the carotid sinus and aortic arch adjust heart rate and vessel tone to keep brain perfusion steady. Stand up quickly, and those receptors trigger faster beats and tighter arterioles to guard against fainting. Bones remodel according to load through a balance of osteoblasts, laying matrix, and osteoclasts, resorbing it. Habitual weight-bearing preserves mineral density, while disuse hastens loss. Anti-gravity muscles the soleus and gastrocnemius in the calves. The quadriceps, gluteals, and spinal extensors maintain tone by resisting Earth's pull with each step and shift. The vestibular system in the inner ear uses otolith organs, with calcium carbonate crystals atop hair cells to detect linear acceleration and head tilt, while semicircular canals sense rotations. Their signals fuse with vision and neck proprioception to stabilize gaze through the vestibulo-ocular reflex, keeping words clear as the head moves. Remove weight, and the same systems adapt quickly, then degrade. In microgravity, fluids redistribute toward the head, producing facial puffiness, nasal congestion, and a rise in intracranial pressure surrogates. Some astronauts develop a constellation of eye findings: optic disc edema, globe flattening, choroidal folds, and refractive shifts, grouped as spaceflight-associated neuroocular syndrome. Calcium begins to leave the skeleton because mechanical loading is absent. Hip and spinal sites can lose on the order of 1 to 2% mineral per month on long missions without countermeasures, a pace resembling severe osteoporosis. Muscles atrophy, especially slow-twitch fibers that normally hold posture. Peak power and endurance fall, and tendon stiffness changes. Cardiovascular reflexes decondition because the heart no longer pumps against a column of fluid. On return to gravity, blood pools in the legs, and orthostatic intolerance appears until training restores tone. Space motion sickness emerges in the first days aloft as vestibular cues and vision disagree, then fades as the brain recalibrates its expectations. Countermeasures make gravity when gravity is gone. Astronauts use resistive exercise devices that mimic heavy lifting through vacuum cylinders and flywheels, preserving hip and spine loading. Treadmills with harnesses apply body weight forces, sout careful light control. Crews use scheduled bright light, dim evenings, and sometimes melatonin to anchor internal rhythms. Noise, CO2 levels, and temperature can fragment rest. Consistent night blocks and personal sleep stations help. After landing, morning light exposure and regular meal timing speed realignment. On the Moon's 1/6 G, or Mars's 3/8 G, partial loading will likely soften but not erase bone and muscle losses. The exact thresholds for healthy maintenance remain a central question for surface missions. Earth-side analogues isolate gravity's role. Bedrest studies with a 6-degree head-down tilt reproduce fluid shifts toward the head and bone loss in loaded regions, allowing controlled trials of exercise, nutrition, and pharmacology. Head-down tilt also tests countermeasures for orthostatic tolerance, since baroreflex deconditioning appears in weeks. Short-arm centrifuges generate artificial G at the feet. Intermittent sessions show promise for preserving cardiovascular function, though optimizing session length and spin comfort remains under study. Gravity guides development as well as maintenance. Embryos form vestibular organs tuned to 1G. Early postnatal motion calibrates circuits that stabilize gaze and posture. Children's bones strengthen along habitual stress lines, and growth plates sense compressive and tensile forces. Prolonged immobilization or weightlessness during growth can leave lasting deficits in density and alignment. Rehabilitation on Earth uses gravity as a variable rather than a constant. Aquatic therapy reduces effective body weight through buoyancy, so joints can move with less pain while muscles relearn patterns. Tilt tables reintroduce upright posture gradually for patients with autonomic failure or long intensive care stays, retraining baroreceptors and venous tone. After orthopedic surgery, carefully staged loading directs callus formation and prevents implant loosening. Prosthetic design models ground reaction forces to distribute stress safely across residual limb tissues. Osseointegrated systems require disciplined progression, so bone adapts without failure. Even microbes and plants register the pull. Some bacteria alter gene expression and biofilm behavior in microgravity analogues, with changes noted in stress responses and, in a few strains, virulence factors and antibiotic sensitivity. Spacecraft water systems and surfaces are monitored with these shifts in mind. Plant roots normally use statolith starch-filled organelles to sense direction. Gravity moves the statoliths within cells, biasing auxin distribution and guiding growth downward, while shoots respond oppositely. Without gravity, phototropism and hydrotropism dominate. Lighting, moisture, gradients, and airflow are arranged to steer roots and stems in controlled agriculture modules. Leaf movement and stomatal timing still follow circadian programming but need environmental cues to maintain phase when dawn and dusk blur. Kidneys and immunity sit in gravity's web as well. Calcium released from bone increases urinary load and the risk of kidney stones. Hydration, citrate, and diet moderate that hazard. Red blood cell mass can fall in flight as the body sheds what seems like excess volume, then must rebuild after landing. Elements of immune function shift in microgravity. Some surveillance pathways dampen, latent viruses can reactivate, and wound healing may slow, requiring careful hygiene and vaccination schedules in crew plans. Radiation is a separate stressor outside the magnetosphere, but its effects interact with bone and marrow, so medical systems treat loading, shielding, and nutrition as a single package rather than isolated tasks. A few images help only to center the pattern. Think of gravity as a quiet rehearsal director. When present, each section plays on cue. When absent, instruments drift until a metronome returns. Then set the image down and notice the practical through line. Provide load and bone listens. Provide resistance and muscle answers. Provide light at the right hour and sleep deepens. Provide upright time and vessels learn again to hold pressure. The adjustments are small each day and decisive across weeks. Another lantern appears in this corridor of facts: companionship through constraint. Gravity sets boundaries the body learns to trust. Remove it, and the systems search for a new normal. Restore rhythms, a dose of weight, a window of bright morning, a span of dark, a steady meal, and they return toward balance. The pull we rarely notice is also the scaffold that keeps many clocks in us aligned. When it softens, care can replace it for a while. When it returns, the body remembers, and the monitors settle back to their patient, even tick. A faint trajectory glows against a dark console, threads crossing like quiet silk. In that stillness, gravity becomes a guide rather than a weight. Rockets lift with fire, but fuel runs out quickly because propellant must push propellant, a truth wrapped in the rocket equation. So mission designers lean on the steady numbers of celestial mechanics. A spacecraft that swings behind a moving planet can leave with more heliocentric speed. One that passes in front leaves slower. No engine adds energy during the turn. The exchange happens because the craft samples a little of the planet's orbital momentum around the sunday. In the solar frame, the bookkeeping is exact, and the result is a change worth kilometers per second. The method is gentle and powerful. Voyager 2 stitched 4 assists into a single grand tour, using a rare alignment of the outer planets that repeats roughly every 176 years. Jupiter bent its path toward Saturn. Saturn bent it toward Uranus. Uranus, in turn, opened the door to Neptune. New Horizons gained years of travel time by dipping through Jupiter's deep well and leaving with a higher speed. Juno borrowed energy from Earth during a long loop to meet Jupiter with a precise aim. Cassini spiraled to Saturn with a chain of passes past Venus and Earth, then used Titan again and again as a movable anchor to reshape its orbit. Messenger needed the opposite trick. Mercury is small, but it orbits very fast, near the Sunday. Arriving from Earth, a probe must shed a great deal of heliocentric speed. Messenger managed that with multiple flybys of Earth, Venus, and Mercury itself before the final burn into orbit, trading time for the missing propellant. Between assists, transfers favor efficient arcs. A Hohmann transfer changes a circular orbit to a new one, with 2 short burns, one to raise or lower the opposite point, and one to circularize on arrival. For very large changes in radius, bielliptic transfers can save propellant at the cost of longer flight times, because slower motion far from the sun makes modest burns count more. Where gravity is strong, a burn at periapsis returns extra energy, the Oberth effect. which deepens or speeds a craft for the same impulse. These are not tricks. They follow from conservation of energy and the way orbital speed varies with distance. Mission software folds in the real complexities: the full N-body pull of many worlds, the non-spherical gravity of spinning planets, the push of sunlight on broad surfaces, and the thruster firings that keep antennas pointed and panels lit. Some paths replace short, sharp burns with months of whispering thrust. Electric propulsion, like the xenon ion engines flown by Deep Space One and Dawn, trades force for endurance. The exhaust leaves at tens of kilometers per second, so each kilogram of propellant turns into more momentum than chemical fuel can offer. Dawn used that thrift to spiral out to Vesta and then on to Ceres, reshaping its orbit slowly and precisely. Solar sails change momentum with photons alone. The pressure is tiny yet continuous. Icaros unfurled a thin square near Venus and steered with reflectivity panels. Lightsail 2 raised its orbit by turning its sail at the right points, using sunbeams as a permanent breeze. A single image helps. Think of sunlight as a fine rain, and a sail as a hand turned to catch it. Gravity narrows destinations in other ways. In the rotating frame of two large bodies, there are 5 points where gravity and the centrifugal effect balance for a small third object. Near the Earth-Sun system, L1 sits sunward and offers continuous solar views. Soho and Discover park there to watch the solar wind and storms before they reach Earth. L2 lies farther from the Sun in a thermally calm shadow with a clear view of deep space. The James Webb Space Telescope loops around it in a halo orbit that stays out of Earth's shadow while keeping a stable, cold attitude. Planck, WMAP, and Gaia also worked from L2, taking advantage of L. Steady temperatures and gentle station keeping. The orbits around L1 and L2 are not static points but graceful loops, maintained with small burns that counter solar pressure and tiny drifts in the multi-body field. Near the Moon, dynamics grow delicate. Weak stability boundaries divide regions where small pushes can lead to very different futures. Ballistic lunar transfers use these boundaries to let a spacecraft drift into capture with minimal propellant, arriving slowly instead of braking hard. The He-10 mission demonstrated such a low-energy capture. Grail traced faint paths to twin lunar orbits to conserve fuel for mapping gravity. These designs look meandering on a plot, yet they respect limits set by mass and energy while expanding what is possible for small spacecraft. Arrival is another conversation with gravity's terms. Entry, descent, and landing depend on local pull, air, and speed. On Mars, thin atmosphere forces layered methods, heat shields to survive hypersonic entry, supersonic parachutes to slow through a narrow regime, powered descent to manage the final kilometers, and, for heavy rovers, sky crane systems that lower the payload on tethers while the descent stage hovers. Curiosity and Perseverance reach the ground this way, timing each stage to the planet's G and the resistance of its air. Comets and asteroids challenge in the opposite direction. Gravity is so weak that a footfall risks rebound. Philae's harpoons failed to anchor on 67P divided by Churyumov-Gerasimenko, and the lander bounced until it came to rest in shadow, proof that microgravity demands new habits for anchoring, hopping, and drilling. On airless worlds with stronger pull, like the Moon, landers throttle through the terminal phase and touch down on plumes that fling dust, that can blind optics and abrade surfaces if not managed carefully. Deep space navigation is patient and exact. Ground stations send radio tones and measure the return time to meter the distance. Doppler shifts, in that tone, reveal line-of-sight speed to millimeters per second. Differential one-way ranging compares the arrival of a coded signal at widely separated antennas improving angle on the sky by timing correlation. Optical navigation adds star fields and images of the target to refine approach geometry. When light, travel time, and geometry make radio alone less certain, all of it depends on synchronized clocks and calibrated delays. Engineers account for the way signals slow through air, cables, and electronics, and for the way relativity nudges seconds on the ground and in flight. The numbers feel clinical, but the mood is calm. Gravity keeps its promises when given accurate initial conditions and small, timely corrections. The emotional center is companionship with a law that does not wander. Navigators set windows years in advance and watch craft thread needles after billions of kilometers, arriving close enough to see ring gaps and dune ripples. The discipline grants confidence. If the burn is on time, the arc will meet the planet. If the pass is shaped well, the speed will change as planned. Fuel stays for the work that cannot be borrowed from motion. And when a mission ends, it ends cleanly, with a final dive or a gentle drift to a stable graveyard that respects the next traveler. Coals dim beneath a grill. Warmth rises without hurry. Gravity and temperature share a steady partnership through buoyancy, convection, and layering. In any fluid, heating makes parcels expand and lower their density. Cooler parcels contract and grow heavier. Lighter parcels rise while heavier ones sink, and the exchange transports heat without stirring the whole medium at once. Earth's weather is built on that exchange. Warm, moist surface, air lifts, cools as pressure falls, and condenses into towering clouds whose tops spread where upper winds guide them. Broad circulation cells move energy from equator toward poles under the quiet steering of rotation, and jet streams form where temperature contrasts sharpen the flow. The same rules shape everyday air. A sun-warmed wall creates an updraft you can feel. Evening ground cools, settles air, and draws downslope breezes into valleys. Oceans move heat more slowly, but carry it farther. At high latitudes, surface water turns cold and saltier as sea ice forms, grows dense, and sinks. That water creeps along the seafloor for thousands of kilometers before rising elsewhere. A thermohaline conveyor that stores heat and dissolved carbon for decades to centuries. Winds push surface layers into gyres, upwelling nutrients along coasts where deeper water is pulled to light. The pattern is not a single loop, but many linked branches with predictable tendencies. Gravity supplies the weight. Differences in density supply the motion. Rotation keeps the curves organized. Inside planets, pressure and temperature climb with depth because overlying rock adds weight. Under those conditions, solids can creep over long spans the way glass sags in time. Earth's mantle convects at centimeters per year, hauling cold slabs downward where plates plunge and raising hot plumes that feed persistent hotspots such as Hawaii and Iceland. The engine runs on leftover heat from assembly and the steady contribution of radioactive decay from uranium, thorium, and potassium. When internal heat falls below the loss to space, convection weakens. Smaller worlds cool faster because their surface area is large compared with their volume. Mars shows thick, quiet crust and tectonics that largely stalled long ago. On the giant planets, internal heat rivals or exceed sunlight. Jupiter and Saturn radiate more energy than they receive. Deep convection, fast rotation, and stratified layers combine to make banded jets and storms that can endure for centuries. Stars bind the lesson to light. Gravity compresses gas until fusion ignites in the core. Pressure from heat then balances the inward pull, a state called hydrostatic equilibrium. Energy moves outward by radiation, where matter is transparent enough, and by convection, where opacity rises. The sun's outer layers boil in granular cells 1,000 kilometers wide that rise, cool, and sink on minute timescales. Red dwarfs mix almost from core to surface. Efficient stirring stretches their lifetimes to trillions of years. In massive stars, radiation pressure becomes important. Envelopes grow turbulent, and fast winds peel mass away. When fusion fuel in a core is exhausted, balance fails. Cores contract and heat until new reactions begin, or collapse advances to white dwarfs, neutron stars, or black holes, depending on mass. The same physics guides comfort at home. Chimneys draw because hot exhaust is buoyant. Cooler outside air replaces it at the fire, and the column becomes a pump. Radiant floors warm objects and feet first, so rooms feel pleasant at lower thermostats. Clothing traps still air, thinning convection from skin. In microgravity, buoyancy vanishes and convection quiets. Candle flames become small blue spheres as heat diffuses evenly. Soot production drops because oxygen is not swept upward. On spacecraft, fans move air so carbon dioxide does not pool around a sleeping face, and heat loads can reach radiators that shine their energy to space. Habitability rests on these ties. Gravity sets surface pressure, which fixes the range where liquid water is stable and controls how quickly air thins with height. Convection in a conducting core drives magnetic dynamos. The resulting field deflects solar wind and helps retain atmosphere. Mars, with weaker gravity and a cooled interior, lost most of its global field early, and then much of its air to sputtering and escape. Titan keeps a thick nitrogen atmosphere because temperatures are low and loss rates are small, even though gravity there is modest. Where interior heat remains, volcanism and tectonics recycle gases, build relief, and sustain the gradients that climates use to move energy. As the evening settles, the theme feels familiar. Gravity organizes mass into layers. Temperature animates those layers with motion. Together, they move energy from where it is made to where it is needed. Clouds lift and rain, currents turn and return, mantles rise and sink, and stars temper their own weight with light. The partnership is plain, and the warmth it carries is patient. Twilight pools in a dry basin. The first star appears without rush. Gravity and expansion write a long, careful forecast. Within galaxies, gravity keeps its local promises. The Milky Way and Andromeda are closing the gap on a schedule of a few billion years, guided by mutual pull and the slow drag of their dark halos. Simulations show a measured dance. Long tidal tails unspool, gas compresses into bursts of star formation, and the two central black holes spiral inward and feed before settling inside a single, relaxed elliptical. The solar system is expected to ride along inside this blended remnant. Planetary orbits should remain mostly intact, though distant comets in the Oort cloud may scatter when passing stars shuffle the outskirts. Beyond our neighborhood, galaxy groups remain bound by their shared gravity, while the larger cosmic web stretches because dark energy continues to drive acceleration on the widest scales. Stars follow internal clocks set by mass. Blue, massive stars burn fuel quickly, live only millions of years, and often end as supernovae that leave neutron stars or black holes. Suns like ours spend roughly 10 billion years on the main sequence, swell into red giants, shed their outer layers as planetary nebulae, and leave white dwarfs that cool for trillions of years. The smallest red dwarfs burn so efficiently that none has yet reached its end. Their eventual remnants, black dwarfs, have not formed because the universe is still too young. Planets migrate under tides and stellar winds. Some drift inward and are consumed. Some are flung outward into interstellar night. Over vast spans, repeated encounters, trade energy, and angular momentum, until compact remnants and long-period wanderers dominate what remains. black holes endure the longest. Quantum theory predicts Hawking radiation, a faint emission that makes them evaporate over unimaginable timescales. A stellar mass black hole could take on the order of 10 circumflex, 67 years to fade. A supermassive one requires far longer still. Long before those epochs arrive, ordinary starlight will thin as fuel runs out across galaxies. Brightness will be punctuated only by occasional mergers, rare accretion flares, or particle decays that whisper rather than blaze. If dark energy behaves like a cosmological constant, expansion continues gently and steadily. If it varies, other fates slow turnaround or rapid rip-enter theory with uncertainty. Current observations favor continued acceleration without drama on human timelines, a background change that leaves tomorrow's sunrise untouched. Closer horizons matter more. Gravity hazards are planned for in years, not eons. Asteroid deflection strategies build in lead time. Kinetic impactors can nudge a small body by centimeters per second and still shift an impact point off Earth years later. A gravity tractor hovering mass that tugs gently adds another option when patience is available. Satellite constellations model orbits under drag. Earth's oblateness, solar radiation pressure, and lunar and solar tides to prevent slow drift into debris fields. Space traffic rules use these predictions to schedule collision avoidance and controlled re-entries. Coastal cities fold gravity data into climate risk. Satellites such as GRACE and GRACE-FO measure mass changes directly, revealing ice loss from Greenland and Antarctica, aquifer depletion under farming belts, and post-quake readjustments of crust. Those gravity maps pair with records of thermal expansion to sharpen sea level forecasts for levees, ports, and wetlands. Civil structures quietly honor gravity as well. Building codes assume local G and seismic risk when sizing foundations, testing soils, and tuning dampers in tall towers. Dams and bridges calculate hydrostatic loads, uplift, and resonance with gravity in every equation. Even small variations matter in precision work. Geodesy ties height to the geoid, an equipotential surface defined by the gravity field, so that a pipeline crossing a continent slopes exactly as intended. In laboratories, optical clocks now sense gravitational potential differences across a few centimeters, letting surveyors read elevation by comparing time itself. One short image helps. We can weigh a hill by listening to seconds. The feeling that emerges is steadiness. Gravity persists as conditions change. It holds memory without judgment. Craters on airless worlds, ripple marks turned to stone, delicate lensing arcs that sketch a cluster's mass. It sets boundaries and leaves choices inside them. Our tools now hear its smallest whispers. The fall of a corner cube in a vacuum, the phase of a cold atom, the stretch of a kilometer-long laser arm as readily as harbors read the daily tide. The far futures do not ask for fear, they ask for patience and for care in the near field where gravity's numbers guide ships, keep roofs honest, and let orchards know when to bloom. And in that patience, the night remains kind. Gravity has been a companion in every scene. The feather and the hammer in a vacuum, the moon tugging two bulges of water around a turning earth, the clock that gains a whisper of time when lifted a few stairs, the star's light bent just enough by the sun to slide a fraction on a plate of glass. It is not a hand but a shape, not an argument but a framework that holds. Where mass gathers, time slows a little and paths curve. Where mass thins, seconds widen. Satellites trust those differences to bring you home. Physicians trust them to time pulses. Geodesists trust them to weigh mountains and aquifers by feel alone. In larger rooms, gravity builds and remembers. Dust becomes worlds. Halos cradle galaxies. Black holes ring like struck bells when they merge and then grow silent again. Dark matter remains unseen and still undeniable in its steady influence. The constant G resists our most careful attempts to pin it down, a reminder that even old truths can keep their edges. Yet nothing in this story demands haste. The same equations that describe a ring of light around a giant hole also forecast tomorrow's tide chart, and both arrive on schedule. If a theme threads through the facts, it is companionship. Gravity is the quiet neighbor who never leaves, who keeps the streetlights upright and the roofs square, who says little and changes almost nothing from day to day, and who, over years, shapes the neighborhood entirely. Take one more breath at this easier pace. Let the numbers dim to outlines. The oceans will keep their appointments with the moon. The satellites will keep their time. You can close your eyes, knowing the frame will be there when you wake, steady as a shore you trust.